So, dear students, we'll further proceed in the uh, vibration measuring, in some two degree of freedom systems. For more cases, uh, like other cases of simple two degree of freedom systems. Okay, so first example we'll take two masses fixed uh, on a tightly stretched string. We'll take few examples of 2D systems and we'll solve the equation of motions. So first case is two masses fixed on a tightly stretched string. Okay. Let's say uh, we have a string fixed on both sides. On the string we'll consider two mass. Let's say M1 and M2. Say this is Y1 and Y2. Now let's say this length is L1, this is L2, between the 2 point masses it is L2, and this part is L3. So we can write here, consider two masses fixed uh, on a tight string stretched between two supports and having tension T. Okay. Now, so if you draw the free body diagram of both the point masses, let's say for point mass M1, uh, this is the tension T at an angle of phi 1, okay, and this is tension T inclined with horizontal at an angle phi 2. This is the acceleration y1 double dot. Similarly for mass m2, this is tension T okay. This one is also tension T, and this angle will be same as phi 2, and this angle will be phi 3. The direction of acceleration in this case it will be y2 double dash. Okay. Now let the amplitude amplitude of vibration is small and tension T is large. Okay, so we can write at any instant, at any instant, let y1 and y2 be the displacement of two masses respectively. The equation of lateral motion of mass of both the masses, we can say, are we can write them as m1 y1 double dot plus t sine phi 1 plus t sine phi 2 is equal to 0 for the first mass. For the second mass, it is m2 y2 double dot plus, it will be minus, okay, minus t sine phi 2 plus t sine phi 3 is equal to 0. Let's say this is our first set of equation. Now from the geometry we have, we can write that sine phi 1 is y1 by L1, sine phi 2 will be y1 minus y2 by L2, and sine phi 3 will be obviously y2 by L3. Let's say this is our second set of equation. Now substitute these values of equation 2 in equation 1. So we can write, substituting the values of equation 2 in equation 1, will have m1 y1 double dot plus t y1 by L1 plus t y1 minus y2 divided by L2 is equal to 0. Subsequently, for second mass, m2 y2 double dot plus, it is minus t y1 minus of y2 divided by L2 plus t uh, y2 by L3 is equal to 0. Or we can write m1 y1 double dot plus t by L1 plus t by L2 y1 is equal to t by L2 of y2 and m2 y2 double dot plus t by L2 plus t by L3 y2 is equal to t by L2 of y1. Okay, let's say this is equation 3. Now assuming a steady state solution for principal mode of vibration as y1 equal to capital Y1 sin omega t and y2 as capital Y2 sin omega t, uh, will have the velocity y1 dot as omega y1 cos omega t, y2 dot will be omega y2 cos omega t, y1 double dot will be minus omega square y1 sin omega t, omega 2 double dot will be minus omega square y2 sin omega t. Now let's say this is equation 4. Okay. Now substituting the values in equation 3, we'll have minus m1 omega square y1 sin omega t plus t by L1 plus t by L2 of capital Y1 sin omega t is equal to t by L2 capital Y2 sin omega t and minus m2 omega square y2 sin omega t plus t by L2 plus t by L3 y2 sin omega t is equal to t by L2 y1 sin omega t. Okay, or we can rewrite the equation as minus m1 omega square plus t by L1 plus t by L2 whole into y1 is equal to t by L2 y2 minus m2 omega square plus t by L2 plus t by L3 y2 is equal to t by L2 of y1. Let's say this is our set of equation 5. Now from equation 5 the ratio of amplitude the ratio of amplitude of vibration can be obtained as uh, y1 by y2 is equal to T by L2 divided by T by L1 plus T by L2 minus M1 omega square. Okay, let's say this is equation 6. Also we'll have y1 by y2 is equal to T by L2 plus T by L3 minus M2 omega square divided by T by L2. Let's say this is equation 7. Now equating both the equations, equating 6 and 7, we have T by L2 divided by T by L1 plus T by L2 minus M1 omega square is equal to T by L2 plus T by L3 minus of M2 omega square T by L2. Okay, so we can rewrite this equation as T by L1 plus T by L2 minus M1 omega square whole into T by L2 plus T by L3 minus M2 omega square is equal to T square by L2 square. Okay, so you can further rewrite the equation as M1 M2 omega to the power 4 minus M1 T by L2 plus T by L3 plus M2 T by L1 plus T by L2 whole into omega square plus T square by L1 L2 plus T square by L1 L3 plus T square by L2 L3 is equal to 0. Let's say this is equation 8. Okay. Now assuming M1 is equal to M2 is equal to M and this L1 is equal to L2 is equal to L3 is equal to L. Let's say this is 9. We'll have M2 square omega to the power 4 minus M into 2t by L plus M 2t by L omega square plus 3t square by L square is equal to 0. Or we can do one thing. Let us write in this way. Let us erase this. Let us erase it and write in a new way. Uh, if you assume this, let's say our ratio will be y1 by y2 will be t by L divided by 2t by L minus m omega square, and also y1 by y2 will give you 2t by L minus m omega square divided by t by L. Okay, let's say this is 10, this is 11. Okay, now if you equate both these equations, we'll have t by L divided by 2t by L minus m omega square, that is equal to 2t by L minus m omega square divided by t by L. So that will give you two natural frequencies, omega n1 as t by ml root over, and omega n2 will give you 3t by ml. One is t by ml root over, another is 3t by ml. Let's say this is equation 12. Yes, 12. Yeah. Now the corresponding principal mode shapes are obtained by substituting in either of the equation this 10 or 11. Okay. So we'll get uh, the first mode shape y1 by y2 as plus 1, and second mode shape y1 by y2 as minus 1. So if we represent them, they will be like this. For the first mode shape, this is y1 for plus 1, this is y2. For the second mode shape, this is y1, then this is y2, y1 plus and y2 minus. So the ratio will be minus 1. Okay. Likewise, the second example, if we take case of a double pendulum. If you take a double pendulum, let us assume we have a rigid support, then first pendulum, then we have the second pendulum. First pendulum mass m1, second m2. Let's say this angle is theta 1, this angle is theta 2, yeah. And length of the first string, let's say L1, length of the second string L2, horizontal distance, let's say x1, and this is x2. Clear? Now for the first pendulum, if you draw the free body diagram, we have this weight acting in downward direction m1g, tension, let's say this is T2, and this tension is T1. This angle is theta 1, and this angle is theta 2. Direction of acceleration, let's say x1 double dot. Okay. For the second pendulum, let's say this is T2, this is the mass, weight acting in downward direction m2g, clear, and the angle with vertical of T2 is theta 2, direction of acceleration x2 double dot, clear. Now let m1 and m2 are the mass of two balls respectively. L1 and L2, length of strings, respective length of strings, you can say. Okay. From the geometry, we have sine theta 1 is x1 by L1, and sine theta 2 is x2 minus x1 by L2. Let's say this is equation 1. Now we have to consider a assumption that considering no vertical motion, and resolving the vertical components, we have T2 cos theta 2 is equal to m2g, and T1 cos theta 1 is m1g plus T2 cos theta 2. Let's say this is equation 2. For small values of theta 1 and theta 2, of theta 1 and theta 2, we can write T2 as m2g and T1 as m1g plus T2 that is equal to M1 plus M2 G. Let's say this is equation 3. Now the differential equation of motion of the two masses in horizontal direction can be represented as m1 x1 double dot plus t1 sine theta 1 minus t2 sine theta 2 is equal to 0, and m2 x2 double dot plus t2 sine theta 2 is equal to 0. Let's say this is our equation 4. Substituting the values of T1 and T2 and sine theta 1 and sine theta 2 in above equation 4, we have m1 x1 double dot plus m1 plus m2 g into x1 by L1 minus m2 g x2 minus x1 by L2 is equal to 0, and as the second mass we can write it is m2 x2 double dot plus m2 g x2 minus x1 by L2 is equal to 0. Okay. So, or we can write m1 x1 double dot plus m1 plus m2 by L1 plus m2 by L2, x1g is equal to m2 L2 x2g. Also m2 x2 double dot plus m2 L2 x2g is equal to m2 L2 x1g. Now assuming let's say this is equation 5. Now assuming a steady state solution for principal mode of vibration, principal mode of vibration x1 as capital X1 sin omega t and small x2 as capital X2 sin omega t. Equation 6. So from equation 6 we can have x1 as x1 dot as omega x1 cos omega t, x1 double dot will be minus omega square x1 sin omega t, x2 dot will be omega x2 cos omega t, x2 double dot will be minus omega square x2 sin omega t. Let's say this is equation 7. Okay. Now substituting the values in equation 5, we have uh, minus m1 omega square x1 sin omega t plus m1 plus m2 by l1 plus m2 by l2 g x1 sin omega t is equal to m2 by l2 g x2 sin omega t and minus m2 omega square x2 sin omega t plus m2 by l2 g x2 sin omega t is equal to m2 by l2 gx1 sin omega t is equation 8. Okay. Now cancelling out the common term, cancelling out the common term of sin omega t, sin omega t from the equation, we have minus m1 omega square plus m1 plus m2 by l1 plus m2 by l2 g g whole into x1 is equal to m2 l2 g x2. Also we have for the second mass m2 omega square plus m2 by l2 g x2 is equal to m2 by l2 gx1. Let's say this is equation 9. Okay, so from equation 9, we have the two values of x1 by x2 as, you can say, first value is x1 by x2 will be equal to m2 by L2 into G divided by m1 plus m2 by L1 plus m2 by L2 G minus m omega square, and the second value x1 by x2 will be m2 by L2G minus m2 omega square divided by m2 by L2G. Okay, let's say this is equation 10, this is equation 11. Now considering m1 is equal to m2 is equal to m, and L1 is equal to L2 is equal to L, we have the ratio x1 by x2 can be written as uh, G by L divided by 3 by L minus omega square. Okay, 3G by L into omega square. This will be equation 12, and x1 by x2 is also equal to G by L minus omega square divided by G by L. Okay, this will be equation 13. Okay, this is equation 12. So if you equate both the equations, you will get this equation omega to the power 4 minus 4g omega square by L plus 2g square by L square is equal to 0 if you equate both of them. So this will give two values of frequency, natural frequency. Omega n1 will be G by L 2 minus root 2, and omega n2 root over, and omega 2 will be G by L 2 plus root 2 whole root over. Yeah, two sets of natural frequency will have. Let's say this is equation 15. Now this gives us two mode sets. One is x1 by x2 as 1 divided by 1 plus root 2. So that will be uh, plus 0.414, and the second one x1 by x2, this is x1 by x2 first mode, x1 by x2 second mode, will give you 1 divided by 1 minus root 2, will give you minus 2.414. Okay, let's say this is equation 16. Now if you plot both the modes for the double pendulum, we have this second mass, This is mass m, this is mass m, this is l, this is l. So the first mode can be plotted as 0.414, and this is 1. And the second mode can be plotted as minus 2.414, and this will be 1. Okay, for the double pendulum. So this one is the first mode, and this one is the second mode, right? So likewise, we can proceed for torsional system. So in the next class, I'll be considering uh, 2 degree of freedom torsional system, how to derive the equation of motion. Thank you.